Let's look at 12.1 sampling and frequency distribution graphs. Here are the objectives. So we're going to look at populations. We are going to look at sampling techniques, how to present and organize data, and then understanding how data can be deceptive. So here are some definitions for statistics. So we are going to collect, organize, analyze, and interpret. Descriptive statistics is just collecting, organizing, and summarizing. Inferential is making general conclusions about the data being presented. Populations and samples. Population set containing all the people or objects whose properties are to be described and analyzed by the data. Sample, subset, or subgroup of the population. Representative sample, a sample that exhibits characteristics typical of those possessed by the target population. So our first example, which we'll use this kind of same example throughout the next couple of examples. A group of hotel owners in a large city decide to conduct a survey among citizens of the city to discover their opinions about casino gambling. Describe the population. So they are going to survey the citizens of the city. So our population would be the citizens of the city. One of the hotel owners suggests obtaining a sample by surveying all of the people at 6 of the largest nightclubs in the city on a Saturday night. Each person will be asked to express his or her opinion about casino gambling. Does this seem like a good idea? So they are only surveying the people at the largest nightclubs on a Saturday night. So think about, what do you think most people who are out having a great time at a nightclub on a Saturday night, what do you think their opinion would most likely be for casino gambling? I think they would be for it. So because they're already at somewhere where there's a lot of people, entertainment, so most likely they would be for it. So it would not be a good idea. And the reason I put is it's only surveying people who attend the nightclubs. They're more likely to be in favor. So it's like a bias sample. So if you want somebody to actually know what do the citizens think, you've really got to do a random sample. So a random sample is obtained in such a way that every element in the population has an equal chance of being selected for the sample. So random is not just one particular group of people. It would be a vast, um, just a lot of different types of people with differing opinions. It's not selecting just one particular type of person. You have to represent the entire population. So you first need to know, well, what is each element in the population? Then you can assign numbers to each element of the population. Randomly select numbers, assign the numbers to the population who have those numbers in the sample set. So that would be considered a random sample. Another example of how someone could collect data is this time the hotel owners decide to only select oceanfront condos in the city. So these are most likely the very wealthy people. They're worried about their property values. So, do you think they would be for or against it? Most likely not. And also, the reason this is not a random sample, which line would be most appropriate way to select a random sample? So, this is a no. It's not giving everyone an equal chance. And that's the importance of having the random sample. Everyone has an equal chance of being selected. This is only selecting oceanfront condos. The next one. What about if they just survey the first 200 people whose names appear in the directory? So that's only going to get last names A through, let's say, well, A through B, maybe. Depends on how big the city is. So that is not going to work. That's not random. The next one, randomly select neighborhoods of the city and then randomly survey people within the selected neighborhoods. So they're going to the neighborhoods, randomly surveying people within those neighborhoods. I think that's pretty random. You're not just picking the really rich neighborhoods or the really, really poor neighborhoods. You're trying to select all of them to represent the entire neighborhood. All right, so let's do a frequency distribution. So what a frequency distribution is it counts the frequency of each item. So this is frequency distribution of the boy's age of maximum yearly growth. Age of maximum growth. So 10, 11, 12, all the way to 18. So let's see, 35 boys is what we have. So we're going to go through here and just do tally marks. That's the easiest way to do a frequency. So we have 12, 14, 13, 14, 16, 14, 14, 17, 13, 10, 13, 18, 12, 15, 14, 15, 15, 14, 14, 13, 15, 16, 15, 12, 13, 16, 11, 15, 12, 13, 12, 11, 13, 14, 14. So after you do your frequency, go ahead and write them down. So this says 1, this says 2, 5, 7, 9, 6, 3, 1, 1. And then you would want to add them up, make sure that your total is 35. So you can do it in your head, or you can do this. Let's see. 1 plus 2 plus 5 plus 7 plus 9 plus 6 plus 3 plus 1 plus 1. 35. So that's a way of double checking that you got everything. So what are some conclusions you can draw about this example? Where's the most? 14. So most boys had their maximum growth, yearly growth at age 14. So they grew the most during age 14. The least would be 10 and then 17, 18. It's all centered around 14 though. So you can write some of those conclusions here if you wanted to. Okay, so that is a frequency distribution. The next one is a grouped frequency distribution. So it says here are the statistics test scores for a class of 40 students. Group the frequencies into classes that are meaningful for the data. Since letter grades are given based on 10-point averages, use the classes of 40 to 49, 50 to 59, and so on. So basically we have A's, B's, C's, D's, and then we have the two different ones that represent F's. So we need to count up how many are between 40 and 49. So you need to look and see. We have 1, 2, 3. So 3 are in the 40s. And you could do the same thing where you do the tally marks. And then 50, go ahead and count those up. I got 6. 60s. Almost just one. That's also 6. Now 70s. 1, 2, 3, 4, 5, 6, 10, 11. 11 is in their 70s. 80s. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And then 90s. 1, 2, 3, 4, 5. Yeah, that's it. 5. Okay, and you want to make sure that we get them all. So 3 plus 6 plus 6 plus 11 plus 9 plus 5. It's 40. So N is the sum of the frequencies, is the number of data items. And it tells you right here that it is 40. So we did it correctly. All right, so let's talk about the vocabulary for this. The class of 49 to 49 has 40 as its lower class and 49 as its upper class. The class width, so that's going from this class to this class, is 10. It is sometimes helpful to vary the width of the first or last class to allow for items that fall above or below most. Okay, so a little bit more on the frequency distribution. It says class width. So we look and see what is the class width between these, and it's 5. The lower class limits are all of these numbers. Lower class limits. You can write them out if you want. Upper class is on this side. Upper class limits. And there we go. Total students. So that'd be your N equals. So we can add these up by hand or with the calculator. There we go. So 10 plus 15 plus 20 plus 16 plus 17 plus 8 plus 7 plus 7 plus 3. I got 103. That's what I did. That's what I got whenever I did it by hand earlier too. Okay, here are a couple other types of ways to show your data. Histogram, so it's like a bar chart. So you would look and see the boy's age of maximum yearly growth. So that was the same data that we had for our frequency distribution, but this is as a bar graph. This is as a frequency polygon, a line graph formed by connecting the dots at the midpoint of each bar on the histogram. Then we have stem and leaf plots. This plot is constructed by separating each data item into 2 parts. The stem consists of the tens digit, the leaf consists of the units digit, so ones digit. So we're going to make this stem and leaf plot. So this is your tens digit, so like 40 what? So we can do our leaf. So 47. Where's another 40? 43. 45. And then we have, I'm actually just going to go one at a time. So that's 82, 75, 64, 57, 82, 63, 93, 76, 68, 84, 54, 88, 77, 79, and 80. 84. I got a lot on the 80s. Oh no, that was supposed to be 94. Do I have an 84? Yeah, I do. I'm going to go ahead and mark that out. There we go. Okay, 92, 94, 80, 94, 66, 81, 76, 67, 75, 73, 66, 87, 76, 56, 57, 74, 50, 78, 71, 59, 76. Okay, so we got them all. The same example that I did before I did this, like my answer key, I put them in order from least to greatest. It's not required, but here's what I wrote. It's still messy, but these are in order from least to greatest. So you can check them that way too. Okay. All right, deceptions in visual data. Graphs can be used to distort the underlying data. The graph on the left stretches the scale of your vertical axis. So see how it stretches that? So it makes it look like this is a huge decline. But if you really look at it, 13.5 to 10.5, is that a huge decline? Not really, but it made it look like it was. The graph on the left stretches the scale of the vertical axis to create an impression of rapidly increasing poverty rate, decreasing. The graph on the right compresses the scale of the vertical axis. So it does that, compresses it a little bit, makes it look like it's slowly decreasing. This should say decreasing, right? Poverty rate is decreasing. Yeah. So things to watch out as you're looking for visual displays of data. Is there a title that explains what is being displayed? Are numbers lined up with tick marks on the vertical axis that clearly indicate the scale? Has the scale been varied to create a more or less dramatic impression than shown by the actual data? Do too many designs or cosmetic effects draw attention from or distort the data? Has the wrong impression been created about how the data are changing because equally spaced time intervals are not used on the horizontal axis? Furthermore, has a time interval been chosen that allows the data to be interpreted in various ways? Are bar sizes scaled proportionally in terms of data they represent? And is there a source that indicates where the data is coming from? Was it a random sample? Who's presenting it? Do they have a special case to make against the trend shown by the data? Here's an example of data that can make you think one way or another. Cosmetic effects of home with equal heights but different frontal additions and shadow lengths make it impossible to tell if they proportionally depict the given area. Time intervals on the horizontal axis are not uniform in size. So we have 1980, 1990, and 2020. So that's 10 years, and then that's 30 years. And it's saying the average size of the home. So look at these shadows. It's saying that the home's going up by what? 200, 340. And then this went up by 312. So this doesn't look as big, but this looks huge. It makes it look like it's a way bigger change. So you just have to be smarter than the chart. You've really got to read into it and make sure that they're not trying to make you think a certain way. And that's all.